Hello guys, my name is Richard. Welcome back once again. So today we are continuing from the thermochemistry. Last time we did states and then we did process functions and stuff like that. Today we're going to move forward from there and do states and state function. But to begin with, just a little bit broad overview of it. So last times we discussed systems, and then we said we have three types of systems: open, isolated, and enclosed. Now these systems can be in a state, and that state that they can be in is determined by the properties. And if any of those properties changes, then we do have what we call a process, or if it's changing any of the properties, it's called a process. So all the properties of a system that defines its state are what we call the state functions. So the state functions over here are properties of a system that defines the state. So I will do this, and then over here say state. For the state, it is the physical appearance, or it is the appearance of the system. So state is the appearance of a system. And then from there we have state functions, right? State functions are properties that defines the states. Now these properties goes pressure, density, we have entropy, enthalpy, we also have Gibbs free energy, and then we have a little bit that we call the temperature and then the volume. So the temperature, and then the volume. These are state functions. There are how many? 1, 2, 3, 4, 5, 6, 7. There are 7 of them. And these defines a state, right? So if a process or if a system changes any of these properties, then it undergoes what we call a process. But for today, we are doing the states and then the state functions. Now, the state functions do not depend on a process, means it doesn't depend on the path change, but they might depend on themselves. For example, this Gibbs free energy depends on enthalpy, entropy, and then temperature. That is why the formula for Gibbs free energy, which is G, is equals to the enthalpy minus the temperature change in entropy over here. So it depends on the enthalpy and then the entropy. They are interdependent. Now, when that is established, we can move on from there and then go to the states. So these systems, right, the system have to be in equilibrium for us to determine the state of the system. So these state functions, they only define the system at equilibrium. It's only at equilibrium that they can define the system. And since systems can be at equilibrium in different temperatures, there had to be a gold standard to which we could compare one equilibrium to the other. And when scientists made that gold standard, they call it standard conditions. So the standard conditions that the scientists made were, for temperature, the standard condition that they made was 25 degrees Celsius or 298 Kelvin. And then they also said that for another condition, if it is a reaction, it has to be in 1 molar concentration, which is 1 mole per liter or 1 mole per decimeter cube. And for the pressure, has to be 1 atmospheres of pressure, right? So these are the standard conditions. So let me put, it was standard standard conditions. Again, the standard conditions was 25 degrees Celsius or 298 Kelvin, 1 molar in concentration, 1 molar, 1 atmosphere of pressure. Now, this is what we said, and you should not interchange this with standard temperature and pressure, which is used for ideal gas. For standard temperature and pressure that is used for the ideal gas, the temperature over here is 273 degree Kelvin. But this is, is 298 Kelvin because it's 25 degrees Celsius. And the other one is 0 degrees Celsius. So once that is put together, under these standard conditions, there are 3 states that the system can be in, which is the 3 states of matter that we do know, which are the solid, the liquid, and then the gaseous state. So that is why a matter, for us to determine the actual state of a matter, it has to be in a standard condition. These are the standard conditions. The MCAT expects you to know, or it's better to know the standard states for some common elements that we may encounter on the MCAT. So elements like elemental hydrogen, which is gas, carbon dioxide, which is also gas, carbon, the solid of carbon, which comes in graphite. You should know water, H2O, which is liquid. You should know sodium chloride, which is also solid. So these are things that we normally encounter on the MCAT, and it is better to know the standard states. And for the standard states, these are the standard conditions. So for the standard state over here, hydrogen gas is just 1 atmosphere of pressure. Hydrogen gas is just 1 molar concentration. Hydrogen gas is just 25 degrees Celsius. Same thing applies to all of these things. The moment you change the states, you change any of these state functions, you undergo a process. And now the system might not be in the same state anymore. That is why it is standard, right? So for instance, if I change the temperature of water, like if I lower it from this 25 degree Kelvin to like 0 degrees Celsius, over here, the state of water changes from solid to from liquid to solid. That's why we have solid ice. When you put ice in fridge, you lower the temperature. So once that has also been established, our next topic, which I am going to link all these together for it to make a perfect sense, is what we call the phase change. Big pressure and volume graph over here. Let me use the black marker over here. This is my y-axis. My y-axis over here is my pressure. And then my pressure is in atmospheres, right? And then my x-axis all the way over here would be the volume. Now my volume will be in liters. Let's say I have a substance, right? I first start with a substance which has a very low pressure and then occupying low volume. So let's say I start over here. And this is a substance which has, let me just, curve it a little bit. I start over here, which over here is basically some pressure. Let me say it's just some pressure. I'm not, putting an actual value there. So just some X amount of pressure, and then started from 0 volume. So from X amount of pressure started from 0 volume over here. Now the system keep on gaining pressure, and it keep on also gaining volume, right? There is a point that I am going to reach over here, right? This point that I reach over here is called a triple point. So let me first name it triple point. Triple point, it is a point in a system whereby all the 3 states of matter can exist. Solid, liquid, gas, all exist over there. So you see, it is some amount of pressure, and then at some amount of volume, theoretically, a system can exist as solid, it can exist as gas, it can exist as also what we call liquid. But let me clean over here. So all these phases, from these phases going, anything that has a very high pressure and low volume, put your mind to it. I have something, that thing is very compacted with pressure, but it is occupying a small amount of space. Those things will be solids. For example, if I have like anything like this marker, the top of a marker, if I'm to expand the particles in this marker, it is trillions, if not billions, but they are occupying a very small space, and the particles cannot really move around each other. They have what we call vibrational energy. They just stand there and then vibrate. So it exists in a solid state. So over here, anything that has a higher pressure, almost zero to nothing volume, or occupy a small volume, over here will be my solid. So any matter that exists within this phase or any system, now we have abandoned the term matter and we're working with system. Any system that exists in this state would be a solid. And then, so for my triple point line, when I get to this point over here, when I get over to the triple point, there is going to be a dot. 50% off their unlimited plan. To anyone who uses the link in my description, it's incognito. At the triple point, there is going to be a divergent, right? The line is going to split into two, where I split one. Let me not go all the way very steep like that. Let me go it this way. Like I split one over here, going that way, and let me do this in a different color. I split one over here, going this way, right? So now I have three lines on my this X, Y, axis, or my Cartesian plane of pressure against volume. Now, let's also cast our mind back. If we have something that has a very large volume, right? Very large volume, but tiny or zero to nothing pressure, what would it be, right? That system would be in gaseous state. Look at the air around us, the atmospheric air around us. It is everywhere, right? And you can barely feel it. If it's not a wind that you are walking through and you're walking through normal and still air, you could barely feel that you're walking through any air. That means it has low pressure. There is no much pressure for it for you to feel it, but it is occupying a high amount of volume, right? So that is, it will be in the phase of gas over here. Now that we have solid and gas phases, what would exist between them would have a moderate amount of pressure and will have a moderate amount of volume. So over here, I am having high temp. It's going to be high pressure, low volume. And then over here at the gas phase, I have high volume and then low pressure. And then existing between these two is the liquid phase. Believe you all have seen it now. The liquid phase. Now the liquid phase is a moderate amount of pressure and then a moderate amount of volume over there. So this is our phase diagram. Now let's do the phase changes as we move from one phase to the other. Now before you really understand what is really happening when we are moving from one state to the other, you need to understand the Le Chatelier's principle of equilibrium. I'm not a French guy. Whatever I say, Le Chatelier, you get it. If you do understand that system, if you do understand what Le Chatelier was trying to prove, you would understand why we have phase changes, or why matter or a system move from one state to the other. Now, for a recap, Le Chatelier's principle states that when a stress is being applied on a system, the system shifts in such a way that the stress will be relieved. That is basically it. You see how Le Chatelier didn't say when stress is applied on a matter. It says when the stress is applied on a system. That is why we're using systems here and have abolished the term matter for now. Okay, let's go over here. So if we have some a particle, right, Let's start with liquid phase. If we have something that is of moderate pressure and then moderate what we call volume as liquid, right? For instance, let's say we have uh, our water bottle, right? In this phase, in atmospheric room temperature, moderate volume, moderate pressure, right? And then we put this into the fridge. Once we put this into the fridge, note that temperature that we have over here as one of the state functions, right, isn't the heat itself. Temperature correlates to the average kinetic energy, right? Like I said in the last discussion, that the average kinetic energy is what also relate to the instantaneous speed of these particles. Now, liquid has a way, it moves, it can slide around itself, it can move around for a little bit, right? So when we put the temperature, since that temperature is related to the average kinetic energy, once we put the liquid or the water inside the refrigerator, we start taking away energy, right? We start taking away. Now, these two things are not state functions. These two things, work, work done, it's not a state function, and heat. This heat here is not enthalpy. That is one issue, that this heat is the actual heat energy, right? That the system can exchange with each other. But you can only determine this heat energy when there are two systems in contact, or when a system changes temperature. That is how we can determine how much heat has been transferred. Right now, I can go off the tangent a little bit over here and then say that if you have a tub of water, like you fill your bathtub with warm water, and then you take a cup and you just collect some of this tap water in a cup, and I ask you to tell the temperature. Will the temperature of the tap be different from the temperature of the liquid that you're holding? No, it wouldn't be, because it is the same water. Let's say it was a boiling water that you fill it, and the boiling water is at 100 degrees Celsius. The boiling water in the tap is going to be 100 degrees Celsius, and the boiling water in the cup is also going to be 100 degrees Celsius. It doesn't matter how much water is there. So heat, temperature itself is an intrinsic property, meaning it is within the matter. It doesn't matter how much of the matter you have. But heat, on this other hand, is not the same. The heat energy of that water in the tap, it is not equal to the heat energy of the water in the cup. This is because when we talk about heat, we require mass. That is why on the long shot, Einstein related energy to mass, where E is equals to mc squared. So the more mass you have, the more energy you have. And since heat is an energy to the tap, which has more heat or more amount of water, is going to have more heat energy than the cup. That is the difference between heat and temperature. Now, heat is an extrinsic property, meaning it is dependence of how much of the substance is there. Comprende? Comprende. Let's move on to what we was talking about over here. So once we put that water into the fridge, we are taking away heat energy. And then the only way that we and heat is like the average kinetic energy that we are taking away. So the particles cannot move around freely. We keep on taking it away, right? And as we say, energy can neither be created nor destroyed. So where is the energy that we are taking going to? Because technically we can't destroy the energy or take it away like that. That is why you should think that when water is cooling down and the particles are, their energy is being reduced and their movement is also being reduced, that energy that is being taken away, it is used to form new bonds between these water molecules. That is why the water changes from liquid to solid. New bonds are being formed. Now, once you have your average water, which is your H2O, have your O here bonded to H, bonded to H, right? In an irregular day, they are all moving around. happily ever after. But once you start taking away the heat energy from them, that heat energy is not like vanishing. It is being used to form new bonds between new hydrogen atoms and new oxygen atoms. So you will see this hydrogen atom is going to bond to a neighboring oxygen atom. But mind you, this oxygen atom has its own two hydrogen atoms, right? This one is also going to bond to another hydrogen atom, and then the bond would keep on going and it will form a crystal lattice. And this crystal lattice is solid that we see as ice. Comprende? Comprende. So once that energy is being used to form these bonds, right? This is where it gets very interesting. Once that energy is being used to form bonds, right, it gets to a point where the temperature, let's say we started with atmospheric or a standard liquid at 25 degrees Celsius or 298 Kelvin. Once we keep on reducing it, now that we are changing the heat, and the only way we can know that the heat is being reduced is measuring the temperature. Once the temperature reaches an equivalent of 0 degrees Celsius, where we say water freezes, something miraculous happens. If the water is to be remain, if the water reaches here, let's say you do not apply any more of the refrigerant to take away the heat energy, and the system is at equilibrium at this 0 degrees Celsius, there is going to be an equal amount of ice as compared to the amount of water. This is how it is going to happen. Say you have your bottled water. This is just, don't mind my drawing. And you have represents the water with blue. You have water over here, which is, in blue. And then you have ice. I'm doing the ice up here because ice floats on water. Ice over here. And the system is at 0 degrees Celsius, right? Or what they call says is at 0 degrees Celsius, right? What happens is that if everything is kept constant in this system, right? The ice over here, let's go with the water over here, right? So the water over here, right, under normal circumstances are going to lose energy, right? Once they lose that energy, they turn into ice. So let's say they lose the energy from 0 degrees Celsius, they will turn into ice. As soon as they turn into ice, that new energy that new mass that have been introduced into the ice section would cause, because there is a new energy, would also cause some of these ice to lose energy, to break the bond. And how would this ice break the bond? They would absorb the heat that this water lost to form the ice in the first place. And once they absorb that heat that water lost to become the ice in the first place, they lose the ice form. And once they absorb that heat, they now also form water, right? So you get like a dynamic equilibrium over there. Now the process of the water losing the heat to go form ice is what we call either freezing or solidification. So if we are moving from liquid to solid over here, we call it freezing. So this arrow points here, we call it either freezing or solidification. And then the water, the ice gaining the heat that the water has already lost to become water itself is what we call melting. So when we move this direction over here, can it be seen? It's called melting, right? So that is for a liquid to a solid transfusion, and from a solid to a liquid transfusion. See how I did all that in just one explanation of a water bottle? Let's move on to the same water bottle, but this time it is not in the refrigerator. So I will erase it, and my water bottle is not in a refrigerator. First, we just start with a regular bottle of water over here. Now, in a regular bottle of water that is sitting in a room temperature, which is the standard room temperature of 25 degrees Celsius or 298 Kelvin, this water over here, right, on the surface of this water, right, something amazing is happening. And this is on the surface of every liquid. It is not just water. On every liquid, the liquid already, as I told you earlier, it has temperature at 25 degrees Celsius, which is correlated to the average kinetic energy. So the particles are already moving. Now, on the surface here, some of these particles that are moving on this surface here are going to gain enough kinetic energy to break the barrier or to break free and become gaseous water. Over here on top of this one will become gaseous water. Now, we did not introduce any source of heat. Of course, the water itself can be gaining a source of heat from somewhere, say the sun, or you put it in the stove, but that is not the point that we are talking about. The point that we are talking about here is that the molecules at the surface of this water gains enough kinetic energy to break free to become gas. Once they break free to become gas, it will keep on breaking and breaking to become gas until it reaches a point, and this is the equilibrium point, where there is enough gas, and then in a regular room where you put a regular water bottle over here, the percentage of water that has to be converted into gas for this equilibrium to reach is 3%. How do I know that? I don't know how I know that, but Google it to see if I'm lying. All right. Okay. So that would be over here. And once that amount of liquid have converted into gas and equilibrium has reached, and the liquid converting into gas over here, let me use the blue, the liquid over here converting into gas, see, from the liquid phase to the gas phase is what we call evaporation. Evaporation, right? Now, once this liquid gain enough energy, so when it reaches an equilibrium, where did it gain this enough energy? That energy is coming from the already gaseous water over here. So this already gaseous water, this would lose that energy, which will be gained by the liquid water, right? And once it loses that energy, it converts back into the liquid. And this process of losing the energy gets back into liquid is what we call condensation. So if we are moving this way, now if you go this way from gas to liquid, we call it condensation. Condensation. Bandawa. All right, now we've done liquid, we've done melting, freezing, condensation, evaporation. One thing that I want to note before we move away from here is that the introduction of boiling points. Right now, as I was explaining the evaporation, right, I did not make a reference, or I said we do not care about where the water is gaining its energy from. But the boiling points is where the introduction of that energy comes in. So let's say this water is being put on a Bunsen burner, right, where it is collecting flames. So let's say it's put on a Bunsen. That guy didn't even invent the Bunsen burner in the first place, but that is not the point. You can Google it too. So you can put on a Bunsen burner, right? Once it's being put in the Bunsen burner, now it is not only the surface that are going to gain enough energy to go to turn into gaseous. It is the entirety of the liquid. So when we ask you what is boiling, boiling is the rapid vaporization of a liquid by the application of an external heat through the entirety of the liquid. So for that, it is evaporation, but through the entire liquid, not just the surface. And this rapid is called vaporization. I even said it in the definition, right? So the vaporization is also converting the liquid to gas. So let's say we come one more over here. Please look at where the arrows point to. That is really important. It's called vaporization. It's called vaporization. Now, from solid to gas, let me move this gas from here and then write it somewhere down here. Gas. From solid to gas. This one, we know I'm not really going to go in depth about it because the phenomenon itself is amazing, right? And it requires some things that are above the scope of the MCAT, which is what we are preparing for over here. So for a solid to move to gas directly without bypassing a liquid phase, you'd say it would require enormous amount of energy for the solid to do that. I know there are some things that, you know, just goes into the gaseous phase from solid phase. Some of these things are dry ice. Dry ice. Dry ice is basically carbon dioxide gas that have been frozen. Once you take it out, it will just go into the gaseous phase from solid to gas. And another one is the naphthalene balls. This is just these scented things that we put in our clothes to make them smell. They are balls. It is solid. When you leave them in the room temperature, that is why you put them in your luggage anyways, just so you know the smell when it goes from the solid. When we go from the solid all the way to the gas, this direction is what we call sublimations. Sublimation. And when we move from gas to liquid, or gas to solid, my bad, we call it crystallization. Pardon my spellings. Crystallization. This might be an I, don't really. Yeah, so when we move from gas to solid, it's sublimation. When we move from solid to gas, it's sublimation. When we move from gas to solid, it is crystallization. We got it? And we've already talked about the triple point where all these state of matter can exist together. Now, the boundary between liquid and solid, this boundary goes all the way to infinity. As long as you keep on increasing the temperature, the pressure, and then the volume, this will go to infinity. But the boundary between liquid and gas terminates at a point that we call critical point. Critical point. The boundary between liquid and gas would terminate at a point that we call critical point. Now, at this critical point, the system is both solid and liquid at the same time. The reason why it is both solid and liquid at the same time, now the name that we give to substances that exist at this place is supercritical fluids. Isn't it like kind of you know, jovial? Supercritical fluids. So that is systems that exist at the critical point. The reason why they exist at a critical point is, imagine this. Imagine you have, let's say, this liquid over here, some liquid, this time not water, just some liquid, and you start applying temperature. Once you start applying temperature, the density of the liquid is going to reduce. Once the density of the liquid is going to reduce, that of the gas up here, if that of this gas up here is also going to increase, right? So as this is being reduced, so as of when we first started, this density was more than this one, and when we started applying heat to the system, or as we started increasing the temperature, the density of the liquid is going to, so density of the liquid is going to reduce, and the density of the gas is going to increase. The point where the density of the liquid, so let me just clean this boiling point, where the density of the liquid is equal to the density of the gas is the point that we call the critical point. And at this point, they all have the same density. So it will be very hard to determine. And if they have the same density, liquid mix. The only reason why we have solutions mixing or different liquids mixing is one, due to polarity and density. So if they have the same density, they will mix. Oil settle on top of water because they have two different densities. If the density of oil was equal to the density of water, they would mix. So if you have two systems which have the same density or two substances here, they will mix, and that point is called a critical point. And a substance that exists over there is called a supercritical fluid. So that is states and state functions for together. Now, let me just do a little bit of brushing. It won't take a little bit long. So first of all, we started with state. We say state is the appearance of a system, or it is the condition that the system is in right now, right? And then we said state functions are properties that defines the state. And the properties that define the state are pressure, density, entropy, enthalpy, Gibbs free energy, temperature, volume. There are 7. I think there is a mnemonic to memorize them. Say, when I am feeling pressured and dense, all I want is to watch TV all day and get hugs. Yes. Yes, this is the mnemonic to get it. When I am feeling pressured and dense, all I want to do is to watch TV all day and get hugs. Hugs. Make sure you add the S. Now the P is the pressure, the D is the density, the T is the temperature, the V is the volume, the H is the entropy, which is H. Oh, the H is the enthalpy, my bad, is the H. The U is the internal energy. See, I didn't even bring it here. So U is the internal energy of the system. And then G is the Gibbs free energy. And then S is the entropy. Understood? So let me put it all here so that you can understand the mnemonic. It says that when I'm feeling pressured and dense, when I'm feeling pressured and dense, all I want to do, that is just to make a sentence, all I want to do is to watch TV, which is temperature, TV, and then V, which is the volume, all day and get hugs. So the hug, the H here, would be your enthalpy. Your U here, will be your internal energy. Your G here will be the Gibbs free energy. And then your S here will be your entropy. Got it? So that is the state functions. Work and heat are not state functions. Okay, once that is corrected, and then we said that when we say states, a state has to be defined as the system at equilibrium. And the system was at equilibrium at 25 degree Celsius or 298 Kelvin, 1 molar concentration, 1 molar atmosphere. And then if you want to bring volume into it, which is really, the volume is not really defined here because it's for standard temperature and pressure. You don't confuse standard temperature and pressure with standard conditions. So because it is in standard, that is why when we write change in Gibbs free energy, we do it like this. This 0 over here represents standard, or zeros, means that is the base point, the standard point. We write enthalpy, change in enthalpy as this. We write change as this. See, the zeros over here means the standard, or it literally means zeros, our starting point. So that is why we have them like that. So once we have all of that covered, we said the system could change from one form to the other. Basically, it would could undergo a process. If it's changing, these things is undergoing a process, but our state functions does not really depend on the process. We talk about freezing or solidification, that is liquid to solid. We talk about melting, that is solid to liquid. We talk about evaporation and then vaporization, that is liquid to gas. We talk about condensation, that is gas to liquid. And then we talked about sublimation, that is solid to gas. And then we talk about crystallization, that is gas to solid. And we also said that the boundary between solid and liquid extends indefinitely to infinity. We also said that, but then the boundary between liquid and gas terminates at what we call the critical point, where the density of the liquid is equal to the density of the gas. And that means the liquid they are the same. You can't differentiate between a solid and a liquid over there. That is a critical point. And a substance at a critical point is called the supercritical fluid. That is all this is about. So I'll do the next, will be the last, video on thermochemistry, and we can move on to other types of, I think, chapter 8, which is, I think, redox reaction or something like that. Thank you very much. My name is Richard. Thank you for watching this video. See you next time. Peace out.